Yeah, it's working.
Can you just can you remember this? Can you no, right? No.
No.
You can connect to this speaker. Yeah.
No, it doesn't work.
It's your.
Yeah, it's mine.
Yeah.
This is right. You're very here. Hey, yeah, it's working. Yeah, I'm just keep saying Do you guys know how to hide this thing? Okay, anyway, I will start at 2 o'clock. So thank you for joining our first reading group. I didn't expect this many people to come. So if you haven't signed in the Excel sheet, please sign up, and we'll probably have to take time to do this thing, but I guess you guys are just trying this first time and see how it works out. So maybe later sign it up, because for today I'm the only one who prepared this review. But if there are more people coming, we can kind of split the times and have a two short review time. So that's kind of our plan. And next week we will not have a reading group because of L4DC and a lot of different things. But we're going to resume week after that, and then the order will be just random, and we will decide in the Google Sheet. Yep. So today I'm going to talk about differential geometry for grasping. So actually, I'm doing two projects. One is the object grasping project, and the other one is the EEG project. But I'm going to talk about this and kind of introduce what I'm doing currently right now. So this is kind of an outline of what I'm going to talk about. Our two main topics will be the shape manifold and the Riemannian manifold. The shape manifold will especially focus on the sign distance function and its characteristic, and one paper related to it. And I'm also going to talk about Riemannian manifold and kind of what it is, kind of an introduction to Riemannian manifold, and very kind of a utility that you can also that will be helpful for your projects also. And I share the two links for these two papers. One is about the Gaussian process for sign distance function, and the other one is for introduction to Gaussian distribution on Riemannian manifold. So if you can read it, it will be better. They have a very good material over there. But today I will just briefly talk about it and kind of tell you how you can use this in your projects also. the grasping. So everyone know what grasping is. So basically, it is it is a basic manipulation that robot can do to carry out the subsequent task, or just do simple tasks such as pick and place and cleaning up the environment. Yes, and it usually and if you go into more advanced grasping, you can actually go into have the robot to use tools, which requires you to grasp certain configuration. So that's what I'm working on right now. But like it's hard to define what a good grasping is. So especially the people who study the primates, who primates use a lot of tools and grasp a lot of things. They have like different behaviors. Usually, what people thought previously was that they grasp the object in a way that they reduce the maximum energy usage. But some papers say that human grasp the object in a way that it doesn't occlude the object that much, so that you can keep your eye on the object. So there are like different perspective of this. But for the robot, the most common things you consider is the object's shape, of course, and the object's pose, and the reachability, which means that if it is reachable in your object robot state, or the manipulability, is it comfortable to grasp in that configuration or not, or of course collisions and such things. And many of those things are related to geometry of the object and the robot, especially grasp object shape is actually one way of manifold, and grasp pose, which is the eccentric poses, are Riemannian manifolds actually, and manipulability is an ellipsoid, or you can think of as a positive semi-definite matrix, which also lies in the Riemannian manifold. And reachability is kind of not a manifold, but collisions have something to do with the shape manifold. So this is kind of a visualization of shape manifold and the Riemannian manifold. So first, I will go into the shape manifold, which is the shape, which is the shape. But like there are like multiple ways to represent the shape in the computer. Especially what graphics people use is the mesh of triangles, or the square rectangles, or the distorted rectangles, which is used in the finite element analysis in heat transfer or fluid dynamics. And there are also point clouds that you're familiar of. RGB cameras are especially lies in this category, point clouds. And there's another way to represent the shape, which is the occupancy or the volume. So there's the occupancy grid, or there's the kind of a slice of the images, which is like a CT images or X-ray images or MRI images or kind of thing. And the density is kind of a probability between 0 and 1. So whenever you're trying to represent some kind of a smoke, how are you going to represent it? It's not a single 0 and 1s. It's like a in between. And it depends on how many air molecules in that voxel area. So it's represented as density. And radius volumes is a light volumes. So especially graphics area represented as harmonic spheres in grid spaces around the environment. But you're probably not going to use it. But if people who are interested in nerve, actually, some people use spherical harmonics like this. But today I'm going to talk about sign distance function, which lies in the surface representation, but it's not like explicit ways like mesh or the point cloud. It's an implicit way to represent the surface. So, and this sign distance function gives you a nice gradient, which you can use for collision avoidance, or actually for object grasping, we can use it for contact analysis, like contact closures or shape closures like that. So yes, so this is like brief introduction of us on this solution. So if ohm is the subset of metric space X with metric D, the sign distance function is this F. So basically this ohm is the surface of the object, and this large X is the Euclidean space. And metric D is the distance function. So basically this means that distance between point X in Euclidean space and the surface of the manifold. And when the point is inside of the object, you just have a flipped signs. So that's the meaning of sign distance function. And if you go into further of what this thing means is actually is the minimum distance between a point X and then point Y, and point Y, which point Y lies on the surface of the manifold. So, and this is one good example of sign distance function, which is like this. So basically, X and Y here are different from this X one here. This is just XY coordinate of the space. So when you look at this circle, the surface is actually this black line, but based on the X positions, its distance changes over the space. And if you're inside, it's actually -1, which is the center of this circle with radius 1. So this is like easy example of sign distance function. So, and like our question is, why do we need this? Like, why do we have to use this? Like, that's because sign distance function has a very nice property in its gradient. So there are three properties. One is the gradient satisfies the Echolocation equation, which means that the gradient can be expressed with this x. But in this case of the sign distance function, it's a constant one. So at every space where you get a gradient, the size will be 1 always. That's the property of the sign distance function. So if you look at this kind of visualization of the sphere, you can see the arrows just spreading out from the sphere, and the size of those are always 1. And the second good property is that the gradient is normal function on the boundary or the surface of the manifold, which means that if your x actually lies on the surface of the manifold, the gradient is the surface normal of that manifold. So when you're trying to do a contact analysis, you can just put a contact point in that gradient function, and then the gradient you get is actually contact surface normal, which can do friction analysis or such thing. And third one is that the gradient is orthogonal to the closest point on the surface, which means that if you just, let's say this axis over here, and if you check the gradient over here, it's actually and flip the gradient and try to go back to the manifold, it's actually the closest point from that initial x. So when you want to get the surface information, for example, and you only have a sign distance function, then you just put a grid points over here, and then calculate the sign distance function and its gradient, which means that you know the distance between these 2 points and you know the direction, you can directly get the original surface points. So that's a good point about it. So first, why is gradient being 1 is good? Like, why is the size 1 is good? This is because even if you don't have a sign distance function, but if you have a function that kind of looks like a sign distance function, such as a Berry function or such like that, their normalized gradient is same as the sign distance function. So for example, if you have a function, monotonic increasing function that goes to origin, which called as a g, it's when you calculate the gradient of it, actually, oh, I forgot to put the partial part here. Actually, if you normalize it, the gradient is same as the sine distance function. So this is actually a really nice property. So if you have some kind of a function that mimics the sine distance function, then you can get this kind of a nice gradient which can be used for collision avoidance. And this is same as what I talked about. You can get a surface normal which is needed for force control or something like that. And getting a closest point on the surface, actually this is not useful for in most of cases, but it is useful for rendering. So in game engines or in kind of those kind of things, they use this sine distance function to render things faster than it should. Yeah, than it normally is in the mesh. So yeah, so when you parse it, it goes to the closest point, and you parse it here, it goes to closest point. Parse it from goes to closest point. If you parse it from here, it goes to closest point. So okay, so then our question is, okay, we get this is something nice, but the problem is how are we going to get it? Like how do we know? How do we get this nice sine distance function? But because like usually what we have is point clouds or depth camera images, which is just gives you a point on the surface, not sine distance function. So easy way to get a sine distance function is actually calculating a distance between all points from the query point, and then just using the closest point. Because as you saw the equation from before, it's basically sine distance is the distance between the x and the closest point on the manifold. So basically, if you measure this, and if point cloud is dense enough, then it's actually a sine distance function. You don't need anything complicated. Of course, you have to have the knowledge that it is inside the object or not, but at least you can get some distance function. But like sometimes you don't have a point cloud that is dense enough to have a nice function. For example, if you're parsing from this point, you'll probably get a distance from here to or here, and get a gradient from here to here. But actually what we want is a gradient, we want to get a distance from here to here and get a gradient from here to here, not like this. So in order to do so, there are many ways to do it. There are actually many ways to do it. You can use the deep learning way to do it. You can use a lot of learning methods or such those kind of things. But one way is using a Gaussian process, which is basically is a supervised learning method that learns the function based on the observations. So basically, and it is very good at doing interpolation. So basically, what we're learning is the function for this each points, and then getting the minimum of that. So it's like a mean function, and inside is the every distance you have. So that's what we're trying to learn from the Gaussian process, and Gaussian process is very good at it, and Gaussian process can kind of do interpolation. So that's why we use the Gaussian process. And the Gaussian process is also used for measuring the uncertainty based on your distribution. But I will not go deep inside it because that is all under the topic. So maybe Jishan in the future will talk about this uncertainty stuff. So maybe we can you can try to know about this Gaussian process later. But the main concept is the Gaussian process is good at learning a function, and it is good at interpolation. That's all we need to know about. So there's a why is the resolution? Okay, so this GPI means the Gaussian process implicit sine distance function. This is this paper does not actually deal with the sine distance function. It just deals with the unsigned distance function. But I will just talk about this because it has good results compared to other Gaussian process implicit sine distance function. So basically, like, how do you get a sine distance from the Gaussian? Basically, there's a kernel function. Usually, Gaussian process a kernel function, and it looks like this. But you know that there's a D here. This is the actual distance from one point to the data points. So basically, their idea was that if we have a kernel function in a Gaussian process like this and make it output and invert this process, basically have an inverse reverting function, which is just inverse function of this, then we'll be able to get this D, which is the distance, then we'll be able to get a distance function. That was their basic idea. So yeah, and these are the equation. And good thing about this is that you can get a gradient of this also. You can just get a gradient of this, which gives you the original sine distance functions gradient. And if you normalize the one is the sine distance function. So yes, so and they say that this learned Gaussian process is the occupancy field around that point clouds. So what they show was that there are many Gaussian implicit methods to do it, but basically what I said, the interpolation in this between these two points are the problems, right? If you're far away, it's kind of approximates, but if you're near here, error increases a lot. But what they did was actually decrease those kind of errors and interpolate it better than other methods. Basically, this Gaussian process interpolator. Yeah. So for my project, I'm using to recover the object's shape with occluded object shapes. So I kind of extended this method and tried to get a sine distance function instead of unsigned distance function. So basically, if you have a full sphere information, you get a good gradient, of course, that's expected behavior. But even if I have a half sphere, I also get a good gradient, like similar to the original one. So this is the sine distance function, and this is the sine distance function of this half sphere, but I'm getting a distance function that looks like a full sphere. So if I have a can, like I can only see a half of the can, I can recover the back shape of the can. If I have a half view of the mustard bottle, I can recover the remaining part. And if I have a half view of the banana, I can recover the remaining parts. Of course, because it is an interpolation method. If I increase interpolation too much, like this, the shape accuracy decreases, of course, because this is the interpolation method. But still, I was able to get some abstract shape. And since I can calculate the uncertainty also using a Gaussian process, I can say how sure or unsure those shape it is. So that's currently what I'm doing. And actually, I'm done with kind of this part and move over to other procedures.
Are you specifying some axis or plane so that the object is symmetry?
No, I'm not specifying. But if you have a 2D view, let's say if you're looking like this, you have pretty much all the views, right? Then you will be able to get most of shapes. But if you're only looking at like this, like without any information from here to here, then the result from this will not be that great. But as long as you have a certain view like this, you will be able to kind of reconstruct the shape. Yeah, but this is usually does not work. But kind of excuses that most of other methods who only have this shape also doesn't work. It also doesn't work. And another good thing is that if I cannot get a good result, I can quantify it using uncertainty. Like I can say how I am uncertain to know. I'm not sure. Can you show me a new view? I can try to do that, or I can do some exploration with the object classifier. So that was all about this shape manifold. Do you have any questions about this shape manifold? Because next one will be harder one.
I have a question like
Yes.
from before for the sign distance function.
Yes.
Like when you are implementing the sign distance function,
Yes.
what is the frame of coordinate? What is the coordinate frame? On which, like, what is the frame on which the sign distance function is based?
It depends on objects. Both.
So means I'm just asking like generally how, like, so,
Uh,
it's like the robot.
Usually, okay, like not many robotics people use sign this function yet, and the active area it is used in the graphics area. So the way that graphics people do it is just put the coordinate in the center of the object. And then if you're, let's say this is your query point X and this is your object, and you set this coordinate over here, right? So, and then you measure this distance. But what if this object's moved like this? Then basically we move this into the object's original coordinate and then queries it again. Then the sign distance function doesn't have to change because x is changing, not this sign distance function.
It may be very naive question, but like, I've seen like in nerve kind of stuff, like the reconstruction, they use truncated sign distance function. If you have seen it.
Yeah.
So how do they do that? Means in nerve, like the object
in
keeps
nerve,
moving.
it is easier because you have a fixed environment.
Okay.
The object is not going to move.
Uh,
The thing is going to move is the x.
so they are doing slam.
Yeah, they're doing slam. So basically, these are moving, and these are every time this thing x moves, you're querying it every single time with the object or the environment.
Okay, but if my object moves,
Object
the-
moves. Think of it as object is static. Like even if object moves, you think of as a x is moving.
so
Yeah,
this
it's a relative position.
so this sign distance function is created on global film.
Yes.
Okay.
Yes. And then and actually there's a discrete sign distance function. So instead of using a function like that, usually you don't have a distance function for this thing, right? How are you going to write the distance function for this thing in this kind of equations, right? So what they do is actually they create a voxel grid around this and they parse the sign distance function and the gradient and then save it as a grid information. And then when they use it, they do a trilinear interpolation. But your voxel only exists in here, right? What if you want to query from this point? Then how you do is actually you query the sign distance and the gradient to this voxel box, and then you do a ray tracing, and then you query the sign distance function in using this trilinear method and query this, and then using a gradient vector like this, you get an original similar to original gradient vector. That's how they do it. They do tracing and query it again. It's a twice sign distance.
So that is called an implicit distance function. It's because it doesn't store the distance, instead they store the gradient or
The one like I talked about.
yes, and also the previous slides.
So the sign distance function is
Is
implicit surface representation. It doesn't store the information of a surface explicitly, but if you have a gradient function, you can get the surface easily. That's the thing. Yeah. Any other question? Okay. Now we're going to the harder one. So this one, I shared the paper previously because you need to read that before this thing, but I'm not sure everyone has read it. But so I will be very slow about it. I will go very slow. So like why did this thing created? Like what is Riemannian manifold and why was it created? It's because Euclidean geometry started not working in some kind of a situations. For example, in 18th century or 17th century, people tried to explore the earth, right? So, and they figured out the Earth is not a flat thing, it's a sphere actually. But when they tried to measure the distance and the angle, they figured out that it doesn't match with the Euclidean geometry. So like the closest point in the sphere might be different than the closest point in those flat maps. So they are wondering, how can we get the closest distance in this kind of a sphere and get to some, colonies, whatever. Yeah. So this is how it started. It started from the cartography, basically, from this mapping thing. So the most important thing in Riemannian manifold is actually measuring the distance. How are you going to get the shortest distance between 2 points on the manifold? That's the biggest thing, and that's probably all you have to know about from this review session. Yeah. So, and this kind of tells you why we need Riemannian manifold. Like for example, we have a sphere. Why can't we just use the sphere coordinates, right? They're sphere coordinates, and it seems like it were going to work well. Like, why don't we use it? Actually, when you try to measure the mean of the sphere coordinates, actually, there are possibilities that you might not get a correct mean. So basically, if you just run naive Cartesian one, you're far off. There's high possibility that the thing is not on the manifold. And if you measure the spherical coordinates, actually, sometimes it gets to a wrong mean when these points are right over here. But if you use the Riemannian manifold, you're able to get the correct mean. So how do you get the mean? It's all about distance. The point that has the lowest distance with these 3 points are the mean. So that's how it works. And usually it's good at measuring the mean on the points of the manifold. Yeah, this is kind of one use case. So and actually quaternion is a Riemannian manifold and kind of started from this thing. And there's also thing called dual quaternion, which also has a relationship with this thing. So this sphere is kind of a direction information. So yeah, how are you going to measure the mean of the quaternion? That's how this thing kind of started. Yeah. So actually, this is kind of a mathematic definition of the Riemannian manifold. This comes out in the paper that I shared. So this paper is kind of introductory paper, so that's what I'm reviewing right now. So I will just go over to it exactly. The Riemannian manifold is actually consists of two things. One is the actual smooth manifold. It has to be smooth. There's a constraint on it, and you need a G called Riemannian metric. But when people say Riemannian manifold, they just express as a single M because it's just easy to write. So when you just see a M, it's actually M and G together. So you can think of this Riemannian metric as the inner product of those points, but inner product of those points in tangent space of the M. So yeah, so there's positive semi-symmetric bilinear form to be like there's a different all different things, but so basically this metric measures the distance between 2 points, not on the sphere, but like a tangent point on the sphere, like it will be the flat space, and you measure the distance there because Euclidean geometry works in the flat space. So they do that and measure the distance, and yeah. So and these are the properties of that metric, where it's a commutative, and if you measure the distance from the same point is always bigger than 0 or equal to 0, and sometimes people write this metric as it's kind of inner product, and when there's a P, it means that it's a measuring this G Riemannian metric on a tangent space from P, and which can be written as the X multiplied by this manifold matrix G on P multiplied by Y. So this is a Riemannian Riemannian geometric matrix. So in that way, you can measure this. So the manifolds that only has this characteristic is called Riemannian manifold. It seems to be very tricky, but there are actually many Riemannian manifolds that you can encounter during a lot of things. So, and there are also this thing. So this is kind of a visualization of the Riemannian manifold. So this is kind of a manifold, and you measure things on the tangent space, which is described as this kind of flat space. So like then if you want to do things in tangent space and go back to the Riemannian manifold, you need a function that lifts this up to the tangent space and lifts this down to the Riemannian original manifold, right? So that those functions are called exponential function and logarithmic function. The exponential function basically lifts this down the tangent space into an original manifold, and logarithm is basically the inverse of that. And there's a very important concept called geodesics. So easily speaking, geodesic is the closest path from one point to the other. So from this picture, this is the geodesic. But when I say shortest distance, it can be a local distance or the global distance, which I will talk about soon later. And parallel tolerance for this, basically, if you have a one tangent space, how do you move to the other tangent space on the Riemannian manifold space? So basically, you have a tangent space here and vector on here. And how do I get the same vector on this tangent space? How do we move things over? How do we have a distance kept but move over to other points tangent space? So if you have kind of took the course Introduction to Robotics, in S3 space, you also talk about kind of exponential and logarithm. So there's actually a connection between them, but actually it's a little different. But you can kind of first understand it as a very similar thing. So the geodesic is the important. So if you have a quaternion here, and if you have a quaternion here, like how do you measure how close are they? Like usually we know that intuitively it's a cosine similarity, right? But that's actually a Riemannian metric. So when you calculate a Riemannian metric, it turns out that the distance between these 2 points can be expressed in a cosine similarity. So how do you measure the distance? That is the geodesic. So, but there's wrong concept about geodesics usually. Geodesic doesn't necessarily mean it's the globally closest path. Basically, as long as it is a straight line on the manifold, it is a geodesic. So you know intuitively that this is the closest, like shortest path between this P and Q, right? But as long as the line is straight on the manifold, this is also geodesic. So, and actually this stems from the physics. So when we talk about black holes, like the definition of a straight line is that there's a zero curvature. You have to go to that point with a constant speed. So basically, what you can think about is the light. Light, according to the Einstein, light has a constant speed, right? So if there's let's say if there's a black hole like this, you know that closest point from here to there is actually this, right? That is also geodesic. But there's another closest path, which is like this. This is also geodesic. So there can be multiple geodesics, and geodesic does not necessarily mean it's the closest point. But in locally, it is closest distance. So when we say geodesic, you usually think of it as the shortest distance. But there are more constraints in it. But in Euclidean space, it's the closest, like it's the shortest path globally. So there.
Even 4 is the closest point?
Yeah, that's geodesic, shortest path locally. So yeah, of course we know that if light first shoots over this way, this will be shortest, right?
Yeah.
But geodesic doesn't necessarily mean globally shortest. Like this one is also locally shortest. So the way you think of it is as a straight line. Shortest, this geodesic is straight line from one point to the other. But the thing is that there are multiple straight lines in this kind of manifold. Yeah, that's a complicated thing. Yeah.
Just wanna ask the question, when you're trying to solve these kind of fortuitous distance
Mm.
problems, why can't you just solve it in a higher dimension? And probably use something like optimization. You know,
That's what they do. That's you go to the simpler space, tangent space, and then use the methods that you can use in the Euclidean space, and then lower it down, and then project into the manifold. So that's all about. Going to tangent space makes you available to do any Euclidean stuff, and then going down to manifold to give you the constraint that it is on the manifold.
I mean, it can be as simple as solving an optimization problem. So, the shortest distance and
No, it's
on the
so
manifold.
if you have a covariance matrix, let's say there's a covariance matrix. How do you measure a distance from one covariance matrix to other covariance matrix? Is it an optimization?
I think you will need a measure.
Metric. That's why you need a Riemannian metric. So that covariance lies on the smooth manifold, and there's a metric, then it becomes a Riemannian manifold. So that metric is Riemannian. That metric is one part of the Riemannian manifold. When you say Riemannian manifold, it's just not a manifold. It's smooth manifold plus the metric. So that's its metric. And metric and geodesic is not exactly the same, but metric decides the geodesic, how geodesic will look like. Yeah. So our question is like, why do we have to use this complicated stuff, right? That's like my biggest question, like why do we have to use this? Like, so actually, like many things in robotics are Riemannian manifold. It's just a form of some kind of representation, and it's metric. So when you think about quaternions, end effector or graph pose, or joint configuration actually Riemannian manifold, and manifold is so uncertainty covariance, inertia and gain matrix, tree structure, like in algorithm, is also Riemannian manifold. So there are tons of things that can be used, but still, why can't we use the existing other methods? Like, right? Like, we don't want to get things very complicated. So this paper talks about three reasons why we should use Riemannian manifold. First, analyze the data on the manifold allows you to reduce the degree of freedom. Basically, when we train the autoencoder or such thing, basically what we do is lowering down the representation of the original input, and then using that to do some kind of a classification or a clustering right there. So basically, by using Riemannian manifold, you can lower down the complexity and do very simple stuff using an existing methods in the tangent space, and then if you lower down to original manifold, it automatically gives you the constrained output that matches with your data's form. And then this kind of a abstract thing, but they said it gives you good understanding about this manifold. Like you have a good understanding about this data, but it's this kind of abstract. And this is actually relevant. If you have a manifold, if you use the manifold, it is easier for you to get rid of the noises that are hindering you from getting a right answers. So you can, for example, if you want to train a GMM, Gaussian mixture model, in this Riemannian manifold, instead of just doing it in Euclidean space, if you do it in here, you can train a good Gaussian mixture model with fewer data points. It's data efficient because you're already considering the constraints of the manifold in your equations. Yes. So
David,
like a lot of concepts are the Riemannian. These are the famous Riemannian manifolds, which is hyperspheres, special orthogonal group, rotation, special Euclidean group, rotation, and the translation, metric positive definite matrix, almost all covariance metrics, not all, like every covariance matrix is metric positive definite matrices. And hyperbolic manifolds, these are the trees and graph. Graph actually lies on the manifold, and Riemannian, and not many people use this, so you can just forget about it. So these are the some famous Riemannian manifolds, and this kind of a Euclidean cross product is possible on Riemannian. So if you have a two Riemannian manifold and just take a cross of it, it's also a Riemannian manifold. So like here's my question: do you think like joint configuration of these two robots are Riemannian manifold or not? This is kind of a trick question, but do you think their joint configuration is Riemannian manifold or not? Is there anyone who can answer this? Just try. It's yes or no. It's a coin toss, right? Yes. Why is it yes? What?
You said that to me a few days back when you were working with grasping.
It's a trick question.
Okay.
It's a trick. You have to be careful.
Okay. Then
So I'll just show you the answer. One is yes, one is no. So actually, joint configuration lies on the hyperspheres, which is the joint revolute joints, right? So, but your phi robot doesn't have a joint limit. Kuka is a joint limit. So if you have a joint limit, it's actually not hypersphere. So it's not Riemannian manifold, but you can set as a subgroup of Riemannian manifold. But your phi, since doesn't have any joint limits, it can be expressed as a hyperspheres. So it's a totally Riemannian manifold. So you can do a joint control in Riemannian manifold.
If it comes on the remote control, you are as you say.
That doesn't depend because hypersphere means every dimension of hypersphere. So if D6 for this is a hypersphere, Kuka is 7, but the thing is it's a constraints hypersphere, so it's kind of a little different. So any dimension, 3, 4, 5, 6, 7, 8, every dimension of this SO3 and SO3 actually, because every dimension of SO3 SOD is a Riemannian manifold, and Euclidean, of course, is also kind of a Riemannian manifold. So any SCD matrices are the Riemannian manifold. Yes, and any size of the positive semi-definite matrices are Riemannian manifold.
what do you mean by no joint limit? What is no joint limit? You said.
So usual robot has a joint limit, right?
Okay, that doesn't have any.
Your phi doesn't have a joint limit.
It can move.
Move 360 again and again like a field. So and actually the light when you studied the introduction in robotics, you heard about Lie theory. So basically, when you convert the rotation matrix or SE3 matrix, you actually make it as some kind of a U matrix or this kind of a shape of the matrix, and then you get this kind of a vector from it. So this is basically Lie theory has an identity tangent space, and then you measure everything from that identity tangent space. But the thing is that, like, okay, then is this the same exponential logarithm that we talked about before in Riemannian manifold? Actually, no. This is just tangent space in identity space. So actually, Riemannian manifold part in here is this part. So when you go from this skew matrix to zeta, which is the rotation vector, then this part is the Riemannian manifold. So there might be confusion, but I'm just saying this to have you not confused with two different concepts. So when you have to move things to the tangent space, when you move things to the tangent space, everything you did in Euclidean space is possible. Calculate the mean, covariance, or clustering in the Euclidean space, or like measuring the distance. Everything is possible. So we can naturally think that, oh, then getting a Gaussian distribution on this manifold is possible, because it's basically getting the mean of the distances and calculate the covariance in tangent space and just lowering it down. So actually, this is the Gaussian distribution on this Riemannian manifold. It's pretty much the same, only you just move things to the tangent space on this mean, and then calculate the x, and then do this, normal distribution calculation. But the thing is that,
Sylvain has a question.
oh, okay, how did she do that? Okay, what is your question, Jaffa?
You can see in the chat.
Okay, do you hear me?
Yeah, I hear you.
Okay, perfect. I had a question about the radius of this sphere, because when you were comparing the Cartesian with the spherical coordinates, you only had the theta and phi for the spheres, and I was thinking even the local or global minimum would be different if we had different radius.
Oh, so when I talk about spheres, it means the hyperspheres, which has a unit radius.
What?
Unit radius. Hyperspheres have a unit radius.
Oh, okay, thank you.
Size of 1, radius size of 1. Yeah. Did that solve your question?
Yes.
Okay. Yeah. So, but calculating mean in Riemannian space is not exactly the easy. So you have to use kind of iterative way, which is described in here. But the kind of essence from this is that you can measure the mean of the S3 poses. You can measure the mean of the orientations. You can measure the mean of the covariance matrix and like all these things. Which means that if you have a mean of the Gaussian distribution and those, you can also do a Gaussian mixture model on this Riemannian manifold. So, and it works pretty much in similar way, but with more iteration for calculating the mean. But this shows how learning this clustering in Riemannian manifold is more accurate than other ways. And of course, if it is able to calculate the Gaussian distribution, you can also do Gaussian conditioning, or creating Gaussian conditioning. You can do a Calinon filter on the Riemannian manifold, or you can calculate the Bayesian inference on the Riemannian manifold. So you can already do all this kind of stuff, and all the maths are already given to you. All those kind of exponential equation and the logarithm equation and transformation equation, they're already all given for this kind of a thing. So what you have to do is just use it, and just do it. So especially this Riemannian manifold is used for evaluating bias signals. So it's this kind of, when you want to control with EMG sensors, then you have a covariance sample covariance matrix between these EMG sensors, and then you can do some kind of a gesture control or something like that. Yep. So conclusion, I will just go to conclusions. This might be my personal thought, but this differential geometry has a lot of potential in robotics, because not many people use this differential geometry in robotics, but they are starting to. So and like, and there's no reason for you to fear about it because most of the maths are already done by physicists or mathematicians, so you can just directly use it. And the sign distance gives you the gradient. The Riemannian manifold gives you a distance metric, which is used for modeling the distribution on weird things that you haven't thought about. Yeah. So that's all, I guess. Oh, and if you want to know more about this differential geometry, there's a professor called Jin Choi in Carnegie Mellon University. And if you go into his YouTube channel or the website, he has all course channels about it. So basically what he does is he does the discrete differential geometry. Basically, when you have a mesh of the object, then you calculate this exponential equation, logarithmic equations, and you do a bunch of your things, like calculating a heat transfer on this manifold and fluid dynamics on this manifold. So this actually kind of automatically cuts the sofa into patches that you can use to make the sofa, or like it has algorithms that automatically unentangles the earphone. There's a bunch of funny stuff. Yep. So that is all for today. Yeah. Any questions? No.
Yeah, I have another question.
Yes. Yes, Shapa.
Okay. I was thinking, do you store what you learned from objects that you're trying to, discover the boundaries of? I mean, you can use the information later to better, better model the occluded parts, right? Or do you compare it to?
You can do that. So
Yeah.
The interesting paper I saw recently was actually using a deep learning method to estimate the polytope of the object using a point cloud. So polytope is actually convex shape units that can be used for contact analysis. So yes, you can use the kind of information.
Yeah, because I was thinking, for example, imagine you're doing the same task tomorrow. You're learning some objects today, and the robot is gonna work again tomorrow, and there is a possibility that the objects are the same, and it can use what it learned the days before. Or maybe you can compare it with a global database of different shapes, different objects.
That's how usually grasping used to work, having a database actually for 5-finger grasping hands. But these days, I think most people move on to like deep learning method and train all those data sets using a single model.
Oh.
Yeah, that's how usually grasping works, using a database.
Mm-hmm. So you're planning to learn new objects every time, right? Actually, that would help with the generalization of the whole process, but I think if you store your own database, that would be useful for your next time.
And there are a lot of existing database also, so we can kind of utilize both existing ones and the newer objects. Yep.
Thank you.
Okay. So I might have spent too much time, but like I just want to quickly discuss about how we're going to do this reading group from now on. So like what is our focus, or are we going to do HRI related stuff or not? How many people are going to do a presentation for a single day? Right now I just did it by myself, but maybe we have more people, we can just do 2-person with just very short presentation for 10 to 15 minutes so that no one has the burden of doing it. So what do you guys think?
It's already 3, so So, yeah, if you are having two presentations, so
It's 10 to 15 minutes. So
yeah, means it should be very short.
yeah, today it was I just had to prepare everything. So are you guys with this time? Are you available in Friday? This 2 o'clock, 2 o'clock-ish. Okay, I will keep this. And for those of you who haven't signed in the Excel sheet, please sign it so that I can just randomize it and have people take turns over to this kind of review stuff. And what you can do review is the ones that you already read or the ones you're studying right now, so that you don't have like extra burden just preparing of this stuff. Today I used the presentation slides, but you can just use some kind of a iPad and just write things down while doing a Zoom or anything else. So yeah, so and the topics, you can do anything that is related to your stuff, but if that can be related to other people's work also, that would be better. So that's kind of a criteria, I guess. And then next week we will not have it, and we're going to have this again a week after next week. Okay, and I will just randomly select anyone who's going to present next time. So don't feel bad about it. It's a random thing. I will just do it totally randomly. Okay, thank you for participating. Okay, I will just end the Zoom now. Okay.